Right now, as you lie here, in whatever darkness you have made for yourself, there is something passing through your body. It is passing through the walls, through the floor, through the entire mass of the earth as though the planet were not there. It does not pause. It does not announce itself. It leaves no trace. This has been happening since the moment the universe began, and it will continue long after every star has gone out. We can see its effects stretched across the cosmos. We can map its gravitational grip on galaxies and on light itself. We can weigh it, and we have. It makes up about 85% of all the matter that exists, and we have no idea what it is. Hello, and welcome to Sidereal. If you enjoy these long stories about space, please subscribe and like the video. I would also be glad to know where you are listening from and your local time. You can leave both in the comments. Tonight, the true scale of the universe. By the end, you will understand why the universe is almost entirely hidden from us, and why that hiddenness is not somewhere far away. It is here, in this room, with you, now. We begin, as all journeys outward must, with light. Light, which seems instantaneous to us, is in fact bound by a strict and finite speed. It is the speed at which information itself travels, the speed of cause and effect. In the 1670s, a Danish astronomer named Ole Romer was studying the eclipses of Jupiter's moon Io at the Paris Observatory. He had access to tables predicting the precise times when Io would slip into Jupiter's shadow and re-emerge. Over many months, he noticed something odd. The eclipses did not happen exactly when the tables said they would. Sometimes they came early, sometimes they came late. The discrepancies were as large as 22 minutes. Romer considered the geometry and realized the timing depended on the distance between Earth and Jupiter. When Earth was farther away, the light from the eclipse took longer to reach him. Light was not instant. It moved. By 1676, he had announced his result to the French Academy of Sciences. Not everyone believed him. His own director at the observatory, the powerful Giovanni Cassini, remained skeptical for years. The finite speed of light was not truly settled until 1679, and then confirmed decisively in 1729, when the English astronomer James Bradley discovered the aberration of starlight, a tiny annual shift in the positions of stars that could only be explained if light travelled at a definite, measurable speed. The speed Romer derived was about 220,000 kilometers per second, not far from the truth. The true speed of light in a vacuum, measured with exquisite precision since then, is 299,792,458 meters per second. We round it to 300,000 kilometers per second. That number is now so fundamental that, since 1983, we no longer measure it at all. Instead, we define the meter in terms of it. The speed of light is not a thing we discovered about the universe and refined over centuries. It is the ruler against which everything else is now measured, and it can circle the Earth more than 7 times in a single second. It is the single tightest limit we know. Nothing carrying information can exceed it. Because light is finite, every glance into the night sky is a glance into the past. The moon you see is just over a second old. The sun is 8 minutes and 20 seconds old. If the sun were to vanish this instant, we would not know it for 8 minutes. We would go on feeling its warmth, seeing its light, orbiting a star that was no longer there. The nearest star system, Alpha Centauri, is 4.3 light-years away. When you look at it, you are seeing light that left just before the pandemic that reshaped the early 21st century. The Andromeda Galaxy, the most distant object visible to the naked eye, is 2.5 million light-years away. The light striking your eye tonight began its journey when our ancestors were early hominins on the African savanna, before our own species existed. You are not looking at Andromeda. You are looking at a message it sent before there was anyone here to receive it. This backwards view extends far deeper. The powerful telescopes of the Hubble and Webb observatories have captured galaxies whose light has been travelling for more than 13 billion years. They appear as they were when the universe itself was young, a small fraction of its present age. And yet that is not the limit. There is a horizon, a wall that no instrument can see past. It is not a wall of matter, but a wall of time. The universe is 13.8 billion years old, give or take a few tens of millions of years. A simple calculation would suggest that the furthest we can see is 13.8 billion light-years in any direction. But the universe is not static. It has been expanding since the beginning, and that expansion carries the numbers past intuition. The space through which those ancient photons travelled has been stretching the whole time, pulling the source that emitted them far beyond its original position. The actual size of the observable universe, the region from which light has had time to reach us, is about 93 billion light-years across. The radius, the physical distance today to the farthest points whose light we can in principle detect, is about 46 billion light-years. That is the distance now to matter whose light left it near the dawn of time. It is worth pausing on that word, observable, because it hides something important. The observable universe is not the whole universe. It is only the part close enough that its light has had time, in the 13.8 billion years since the beginning, to reach us. Beyond that horizon, the universe almost certainly continues, and we have no way of knowing how far. It may be vastly larger than the part we can see. It may be infinite. Every observer, anywhere in the cosmos, sits at the center of their own observable sphere, seeing out to their own horizon in every direction. And none of those horizons is a real edge, only the limit of how far light has managed to travel. We are not at the center of the universe. We are at the center of the only part of it we will ever be permitted to see. And the age itself, that figure of 13.8 billion years, is not a guess. It is read from the oldest light with real precision, cross-checked against the ages of the oldest stars and the slow cooling of the most ancient dead suns, 3 separate clocks that agree. We know when the universe began more accurately than we know almost anything about what it is made of. And at that edge, something occurs that sounds like a violation of physics, but is not. The galaxies that sit at the very rim of our observable sphere are not simply receding. They are receding so fast that the space between us and them is stretching by more than 300,000 kilometers every second. They are moving away from us faster than light. This breaks no law, because the galaxies are not hurtling through space at that speed. Space itself, the fabric in which they sit, is carrying them apart. At sufficient distances, the expansion of the universe overwhelms any local motion. The light those galaxies emit today will never reach the Earth. Not in 1 trillion years. Not ever. They have slipped beyond a horizon of cause and effect, permanently disconnected from our future. There are galaxies we can still see tonight as they were in the deep past, whose present-day selves are already lost to us, their current light falling forever into the stretching dark. The oldest light we can see is the cosmic microwave background. It was released about 380,000 years after the Big Bang, when the universe had cooled enough for electrons and protons to combine into neutral hydrogen, allowing photons to travel freely for the first time. Before that moment, the universe was an opaque fog, a dense plasma in which light could not move more than a short distance before scattering off a free electron. The moment the fog cleared has its own name, recombination, and it was less a sudden event than a threshold quietly crossed. For its first few 100,000 years, the universe was simply too hot for atoms to hold together. The negatively charged electrons moving too fast to be captured by the positively charged nuclei, and free electrons are very good at scattering light, so the whole cosmos glowed like the inside of a star, opaque and blinding, every photon knocked sideways almost as soon as it was born. Then, as the expansion cooled everything below a certain temperature, the electrons slowed enough to be caught and bound into neutral atoms, and all at once the fog of free electrons was gone, and light could fly in a straight line across the universe for the first time. When the fog cleared, the light that had been trapped streamed outward, and it has been travelling ever since. Along the way, it has been stretched by cosmic expansion, shifted from brilliant visible and ultraviolet wavelengths all the way down into the microwave band. Its temperature today is 2.7 Kelvin, just under 3 degrees above absolute zero. We detect it as a faint, uniform hiss coming from every direction in the sky. It is a photograph of the universe's infancy, the earliest moment we can ever directly observe. Beyond it, there is nothing to see, only the fog. The cosmic microwave background is the absolute visual limit of our existence. And yet everything we see in that ancient light, every galaxy, every cluster, every filament of the cosmic web, every planet and star and human being, accounts for less than 5% of what the universe must contain. This figure is not a rough estimate. It has been measured independently by several methods that do not depend on one another, by the pattern of the cosmic microwave background mapped by the Planck satellite, by the clustering of galaxies, by the gravitational bending of light. The universe that we call visible, the whole shimmering tapestry of luminous matter, is a thin froth on a vast, invisible ocean. About 27% of the universe is dark matter, a form of mass that exerts gravity but does not emit, absorb, or reflect light. And about 68% is dark energy, a pressure driving the expansion of the universe to accelerate. The confidence in those figures comes from the fact that they are not measured just once. The fine pattern of the oldest light gives one value. The way galaxies cluster across the sky gives another. The bending of light by unseen mass gives a third. The brightness of distant exploding stars gives a fourth. These methods rely on entirely different physics and entirely different instruments, and they have no reason to agree unless they are all measuring something real, and yet they land on very nearly the same recipe. That agreement is why the 95% is not dismissed as a mistake or a fudge. It is one of the most thoroughly cross-checked results in all of science, and it says, plainly, that everything we can see is the small exception, and the rule is a darkness we cannot name. We do not know what either of these things is. The 95% of the cosmos that governs its structure and its fate is, to us, invisible and unknown. The hiddenness is not out there, in the deep reaches of intergalactic space. It is here, in the room with you, passing through your body right now. And before this night is done, you will understand what that means. But first, we must learn to see the scale that we already inhabit. The universe's hidden architecture is built on emptiness that defeats intuition, and the road toward that emptiness begins in our own backyard. If you could drive a car to the sun, holding a steady 100 kilometers per hour without ever stopping for fuel or sleep or food, you would arrive in 171 years. A person born at the start of that journey would grow old, raise children, watch grandchildren age, and die long before the destination came into view. No human lifespan can hold that distance. And yet, in cosmic terms, the sun is right next door. It is the closest star. It is the one we live beside. His drive farther, out past the gas giants, to the orbit of Neptune. At the same steady, impossible speed, without pause, the journey would take you roughly 5,000 years. That is the entire span of recorded human history, from the first clay tablets of Sumer through the building of the pyramids, the fall of Rome, the voyages of the Ming dynasty, the invention of the printing press, the 2 world wars, and up to this present night. All of it would fit between the moment you pressed the accelerator and the moment you finally arrived at the 8th planet. And you would still be deep inside the sun's domain. Beyond Neptune, before the true edge, lies another region worth naming, the Kuiper Belt, a broad, flattened ring of icy worlds and debris left over from the making of the planets, home to Pluto and a swarm of smaller frozen bodies. It was into that belt that the New Horizons probe flew, sending back the first close pictures of Pluto in 2015, revealing a world of nitrogen glaciers and mountains of water ice, a place 4 billion miles from the sun, where sunlight is 1,000 times fainter than we know it, and noon looks like deep twilight. And even Pluto is barely a third of the way to the inner edge of what comes next. The outer edge of the solar system is not Neptune, and it is not the Kuiper Belt. It is a vast, spherical shell of icy bodies called the Oort cloud, extending from perhaps 2,000 times the Earth-Sun distance out to 100,000 times that distance. That reach, 100,000 times the Earth-Sun distance, is close to 1/5 of the way to the nearest star. At 100 kilometers per hour, reaching the outer boundary of the Oort cloud would take you about 17 million years. That is longer than the genus Homo has walked the Earth. It is longer than the entire journey that led from the first upright primates to the being lying here, listening. The solar system alone is a wilderness of emptiness so profound that a human mind, left to hold it without numbers, simply shuts down and quietly substitutes a comforting miniature. If we compress that whole system into a model you could set on a table, the emptiness becomes something you can almost feel. Take the sun as a marble, a single centimetre across. On that scale, the Earth is a grain of sand 2.5 meters away. Jupiter is a small bead 13 meters from the marble. Neptune is another grain, 80 meters out. And the Oort cloud, the true edge, would begin 2 kilometers from the marble sun and end 10 kilometers away. Between the marble and its nearest planet grain, and between every grain and the next, there is nothing you could notice. A wisp of solar wind, a few atoms in each cubic centimetre, the occasional silent asteroid. Oh, to a traveller crossing it, the solar system would be an unbroken blackness, the star fields overhead hanging motionless for a lifetime. The effort to measure even the first rung of this ladder, the distance from the Earth to the Sun, has a history written in human obsession and occasional heartbreak. The method was proposed by the English astronomer Edmund Halley, the same man whose name is on the comet. In 1716, Halley realised that the exact scale of the solar system could be triangulated using the transit of Venus, the rare occasions when the planet Venus passes directly between the Earth and the Sun and can be seen as a tiny black dot crawling across the solar disk. If observers stationed at widely separated points on the Earth timed the exact moments the dot entered and left the disk, simple geometry would give the distance. Halley knew he would be long dead before the next transits arrived. He wrote up the method and left it as an instruction for the astronomers who would come after him, a task handed forward across a generation. The transits of Venus come in pairs, the two events 8 years apart, with gaps of more than a century between one pair and the next. The pair that Halley had pointed to, predicted for 1761 and 1769, ignited what was arguably the first truly international scientific collaboration. Expeditions were sent across the globe by the British, the French, the Austrians, and the Russians. The British sent James Cook and the ship Endeavour to the newly charted island of Tahiti to observe the 1769 transit, a voyage that would go on to map the coast of New Zealand and eastern Australia almost as an afterthought. It was an era of wooden ships, uncertain charts, and frequent war, and the effort to measure the sky sent men to the far ends of the Earth. One of those men was a French astronomer named Guillaume Le Gentil. He set out from Paris in 1760, aiming for Pondicherry, a French outpost in India. By the time his ship neared the Indian Ocean, the 7 Years' War had broken out. Pondicherry was under British siege. His ship was turned away. The day of the transit, the 6th of June 1761, found Le Gentil still at sea, the deck rolling too heavily beneath his instruments for any measurement to be possible. He recorded the moment with a scientist's discipline. He noted the roll of the ship. He noted the uselessness of his telescope on a moving deck, and he resolved to stay abroad for the next transit, 8 years away, rather than sail home and return. He spent those 8 years in the Indian Ocean. He mapped the coast of Madagascar. He survived dysentery and storms. He travelled to Manila and back to Pondicherry, which had by then been returned to France, and there he built a small observatory and waited, watching the weather for months, preparing. The morning of the transit, the 4th of June, 1769, dawned perfectly clear. Le Gentil made his telescope ready, and then, just as Venus began to touch the edge of the sun, a bank of cloud rolled in and covered the sky. It stayed for the entire duration of the transit. The sky cleared again the moment the transit ended. Le Gentil wrote afterwards that he had spent more than 2 weeks in a singular dejection, almost unable to take the least nourishment. He packed his instruments and began the long journey home, only to be delayed further by illness and by a hurricane that nearly sank his ship. When he finally reached Paris, 11 years after he had left, he discovered that he had been declared dead. His estate had been divided among his relatives. His seat at the Royal Academy had been given away. He fought for years to recover part of what had been his. The distance to the sun had been measured, in his absence, by others. Le Gentil, for all his misfortune, at least came home. Another of the 1769 observers did not. A French astronomer named Jean-Baptiste Chappe-Dauteroche travelled all the way to the tip of Baja California, in what is now Mexico, to catch the transit from clear desert skies. He succeeded. He made his measurements cleanly, under a perfect sun, while an epidemic swept through the small settlement around him. He refused to leave his instruments, kept working through the outbreak, and died of the fever shortly after, along with most of his party. Only one member of his expedition survived to carry the observations back to France. When you set these stories side by side, the effort to measure a single distance takes on a weight that the number itself never shows. Men crossed oceans, waited years, went mad with frustration, and died to fix the length of the line between the Earth and its own star, so that every distance beyond it could be built on a firm foundation. The scale of the universe was not handed to us. It was assembled, painfully, one rung at a time, by people most of us have never heard of. The precise value was pinned down much later, and not with wooden ships and patience, but with radar. In the 1960s, astronomers at the Jet Propulsion Laboratory and at the Great Dish at Arecibo bounced radio pulses off the surface of Venus and timed how long the echo took to return. The speed of light was known exactly. The round-trip time gave the distance. The Earth-Sun distance is now fixed at 149,597,870 kilometers. That precision matters because this one length underpins every other distance we measure beyond the solar system. Everything farther out is calibrated, in the end, against the gap between the Earth and its own star. And yet the number itself means almost nothing to the human body. What matters is the emptiness it describes. To feel that emptiness with something real rather than a model, consider the Voyager 1 spacecraft. It was launched in 1977, and it remains the fastest and most distant human-made object ever to leave the inner solar system, moving now at about 17 kilometers per second. As of tonight, it is more than 160 times the Earth-Sun distance away from us. In 2012, it crossed the heliopause, the boundary where the solar wind, the constant stream of charged particles blowing outward from the Sun, finally gives way to the thin, cold plasma of interstellar space. As it crossed, the spacecraft's instruments recorded a sudden drop in the particles streaming from the Sun and a rise in the denser hiss of the galaxy beyond. It was a moment of true departure. For the first time, something made by human hands had left the bubble. The Sun blows around itself and entered the space between the stars. That bubble has a name, the heliosphere, and it is not a neat sphere but a vast, lopsided pocket, blown outward by the solar wind and pushed into a rounded shape at the front, and drawn out into a long tail behind, as the whole Sun and its family plough through the thin gas of the galaxy. Voyager 1 is not alone out there. Its twin, Voyager 2, crossed the same boundary a few years later on a different path, confirming the crossing from a second direction. Ahead of them, silent now, drift the two older Pioneer probes, their signals long since faded, coasting outward on their own endless trajectories. 5 spacecraft in all are on their way out of the solar system forever, the first objects our species has ever sent beyond the reach of its own star, and every one of them will wander the galaxy for far longer than the human species is likely to exist, long after anyone who built them is gone. And yet Voyager 1 has not truly left the solar system. It has merely reached the outermost suburbs. It will not arrive at the inner edge of that same Oort cloud, the icy shell we spoke of, for another 300 years. To pass entirely through the Oort cloud will take it 30,000 years. Long before then, its nuclear power source will be exhausted, its instruments dark, its golden record of human sounds and images spinning on through cold nothing, carrying the greetings of a civilization that will have no way of knowing whether they were ever heard. On that record, chosen by a team led by Carl Sagan, are birdsong and thunder, greetings spoken in 55 languages, a diagram of where the Earth sits among nearby pulsars, and the sound of a human heartbeat and brain, recorded from a woman in love. It was a message in a bottle thrown into an ocean so vast that the nearest shore is 40,000 years away, at the probe's current speed, and even then, Voyager is not aimed at any particular star. It is simply leaving. There was one more thing Voyager did, before it went silent to the outer dark. In 1990, at Sagan's urging, as the probe left the planets behind, its camera was turned around to look back at where it had come from. In the photograph it sent home, the Earth is a single pale dot less than a pixel wide, caught by chance in a scattered band of sunlight, a mote of dust suspended in a sunbeam. Every human being who has ever lived, every empire and war and love and grief, the whole of our history, was contained in that one dim point of light, seen from a distance that is still, by cosmic standards, the near suburb of home. Even this, the whole reach of the sun's domain, is only the first and closest pocket of the void. If the distance between our own planets already outlasts a human life many times over, the question that pulls us onward is simple. What lies between the stars? And beyond them, between the galaxies? To reach the next star, we first had to learn how to measure a distance that no expedition could ever cross. The trick is the same one your own eyes use without your knowing it. Hold a finger up at arm's length and look at it first with one eye, then the other. The finger appears to jump against the background. That jump is parallax, and its size depends on how far away the finger is. The Earth's orbit gives astronomers a much larger version of the same effect. Observe a nearby star in the winter, then again in the summer, from opposite sides of the Earth's orbit, and the star will have shifted very slightly against the far more distant stars behind it. The shift is agonizingly small, and for 2 centuries after the telescope was invented, no one could measure it at all. That failure was itself a kind of evidence, because it meant the stars had to be enormously far away. The first person to succeed was the German astronomer Friedrich Bessel. In 1838, after months of painstaking measurement, he detected the parallax of a faint star called 61 Cygni and calculated its distance. The number he arrived at was staggering for its time, roughly 10 light-years, and it was close to the modern value. For the first time in history, a human being had measured the distance to another sun. From this method comes the astronomer's favourite unit, the parsec, a word built from parallax and second, defined as the distance at which a star would show a parallax shift of 1 second of arc. A parsec is a little over 3 light-years. It is a unit made entirely out of the geometry of our own small orbit, extended outward into the dark. But parallax only reaches so far. The shift grows smaller with distance, and beyond a few hundred light-years even the best measurements run out, the jump too tiny to detect. To go farther, astronomers had to build a ladder, each rung calibrated against the one below it. Parallax fixes the distance to the nearest stars. Those nearby stars reveal the true brightness of certain kinds of star, which can then be recognized much farther away and used as markers in turn. Those markers calibrate the pulsing Cepheids, which reach across to other galaxies. The Cepheids calibrate the exploding stars that can be seen across billions of light-years. Every distance in the universe, out to the farthest galaxy ever measured, rests in the end on that first small triangle drawn from opposite sides of the Earth's orbit. Kick out any lower rung and everything above it falls. It is a remarkably fragile-looking structure to have measured a cosmos with, and it has been checked and rechecked so many times that we now trust it to within a few % across most of its length. Much of the groundwork was laid, again, by the women of the Harvard Observatory. One of them, Annie Jump Cannon, classified the spectra of hundreds of thousands of stars by hand, sorting them into the sequence of stellar types that astronomy still uses today, working with such speed and accuracy that she could classify a star in seconds from the pattern of its light. Deaf for most of her adult life, she catalogued more stars than any person before her. It was that vast, patient, underpaid labour of classification, star by star and plate by plate, that turned the night sky from a scatter of points into a measurable thing. And it is worth remembering that the map of the universe was drawn, in no small part, by people who were paid like clerks and credited like footnotes. With a way to measure it, the true gulf between the stars can finally be stated, and it is best felt by shrinking everything at once. Imagine the sun reduced to the size of an orange, 10 centimeters across, sitting on a table in front of you. On that scale, the entire solar system out to the Oort cloud would fill a region a few kilometers wide around the orange, and the next star, Proxima Centauri, the closest sun to our own, would be another orange, sitting 3,000 kilometers away. From the west coast of Europe, that is the far side of Russia. 2 pieces of fruit, 3,000 kilometers apart, and between them nothing but a few stray atoms in each cubic meter, and a cold that has no bottom. That is not a strange corner of the galaxy. That is the galaxy. That is the average. The stars, in other words, are not a crowd. The average density of stars in the Milky Way is roughly 1 star for every cube of space, a little over 3 light-years on a side, and in our own neighbourhood the spacing is wider still. If each star were a single person, That person would be standing alone in the middle of a continent, the nearest other person an entire ocean away, the one after that on another continent entirely. And yet, from far enough away, all this loneliness resolves into something that looks solid and bright. The Milky Way's few 100 billion stars, spread across a disk, 100,000 light-years wide, blur together into a soft, continuous glow. A band of milk across the sky, a thing that seems substantial enough to have a shape and a name. The solidity is an illusion of distance. Move closer, and the glow dissolves back into separate points of light, each one impossibly alone. For most of human history, this single glowing island was thought to be the entire universe. The idea that there might be other islands, other galaxies scattered through a far greater dark, was a speculation with no proof behind it. And it came to a head in 1920, in Washington. 3. In what became known as the Great Debate. Two astronomers faced each other over a single question. Harlow Shapley of the Mount Wilson Observatory and Heber Curtis of the Lick Observatory argued about the nature of the spiral nebulae, the faint whirlpools of light that dotted the sky in every telescope. Were they clouds of gas within our own galaxy, or were they separate galaxies at unimaginable distances? Shapley argued they were nearby. He had recently done something remarkable in its own right. Using clusters of stars as markers, he had measured the size of the Milky Way and found it far larger than anyone had believed. And, crucially, he had shown that the Sun was not at its centre but far out toward one edge. Having just enlarged the galaxy so dramatically, Shapley could not accept that the spiral nebulae were separate galaxies, because to appear as small as they did at such distances, they would have to be almost inconceivably far away. Curtis took the opposite view. 2. He pointed to the spectra of the spirals, which looked like the combined light of many stars rather than glowing gas, and to the dark lanes of dust that threaded through some of them, just like the dust lanes of the Milky Way. He argued they were island universes, whole galaxies in their own right, millions of light-years distant. Neither man had the decisive proof. History would judge each of them half right. Shapley was correct about the great size of the Milky Way and the Sun's place off to one side. Curtis was correct that the spirals were separate galaxies. The debate ended with the largest question in astronomy still open. What is striking, looking back, is that the two men were arguing about the size of everything, and neither could settle it, because the tools to measure the distances simply did not yet exist in their hands. The whole question of whether the universe was one galaxy or countless galaxies, the difference between a cosmos 100,000 light-years across and one spanning billions, came down to a single number nobody could yet measure: the distance to the spiral nebulae. The argument could not be won by cleverness or by rhetoric. It could only be won by a measurement, and the measurement was, at that very moment, waiting to be made. The evidence that would settle it already existed. It had been sitting in a set of glass photographic plates in an office at the Harvard College Observatory, gathered by a woman whose name most of the men in that debate barely knew. Henrietta Swan Leavitt was one of a group of women employed by the observatory to do the exacting, low-paid work of measuring and cataloguing stars on photographic plates. They were called, without irony, the Harvard computers, because computing was what they did by hand, star by star, for wages a fraction of a man's. Leavitt was assigned to study variable stars, stars whose brightness rises and falls in the two Magellanic Clouds, the small companion galaxies visible from the southern sky. She focused on a particular kind called Cepheid variables, stars that pulse in brightness with a steady clockwork rhythm. By 1912, she had found something buried in the data that would become one of the most important tools in all of astronomy. The Cepheids in each cloud pulsed with different periods, some over days, some over weeks, and Leavitt noticed that the period was tied to the brightness. The slower a Cepheid pulsed, the more luminous it truly was, and the relationship was tight and predictable. Because all the stars in a single Magellanic Cloud sit at very nearly the same distance from us, their differences in apparent brightness had to reflect real differences in output. Leavitt had found a way to read a star's true luminosity directly from the rhythm of its pulsing, and once you know how bright a star truly is, and you measure how faint it appears in your telescope, the difference tells you exactly how far away it is. She had built a cosmic yardstick out of the heartbeat of a star. She published her finding under the modest heading of a remarkable relation between the brightness of these stars and the length of their periods, and she never claimed anything grander for it. The physical reason for the rhythm would only be understood later, a layer of ionized helium deep inside these stars, acting as a kind of valve, trapping heat and releasing it in a regular cycle that makes the whole star swell and shrink. Leavitt did not need the mechanism. She had the pattern, and the pattern was enough to measure the universe. In 1923, at that same Mount Wilson Observatory, a young astronomer named Edwin Hubble turned the 100-inch Hooker telescope, then the largest in the world, toward the Andromeda Nebula. He was hunting for novae, sudden flares from dying stars. On a plate exposed on the night of the 5th of October, he found a star he first marked as a nova. Then, checking earlier plates, realized was something else. It was pulsing. It was a Cepheid variable. Hubble applied Leavitt's yardstick and calculated the distance to the star, and therefore to the nebula that held it. The number came out at roughly 900,000 light-years, far beyond the most generous estimate of the Milky Way's size. The Andromeda Nebula could not be a cloud of gas inside our galaxy. It was a galaxy of its own, a spiral of hundreds of billions of stars, an island universe exactly as Curtis had argued. Hubble sent word to Shapley. Shapley read the letter and, according to a colleague standing beside him, said quietly that here was the letter that had destroyed his universe. He had been wrong about the nebulae, and he knew at once what it meant. The Milky Way was not the whole of creation. It was one island among a multitude. Having found the other islands, Hubble set about sorting them. He grouped the galaxies by shape into a scheme still taught today. The graceful spirals with their winding arms, the smooth featureless ellipticals, the barred spirals with a straight bridge of stars across the centre, and the irregulars with no clear form at all. He arranged them in a diagram shaped like a tuning fork, and although he mistakenly believed at first that it showed a sequence of aging, one form evolving into the next, the classification itself proved lasting and useful. In a single decade, the universe had gone from one galaxy to a zoo of them, and then to a system for naming their kinds. What had been, a few years earlier, a single glowing island thought to be all of creation, was now understood to be one ordinary spiral among billions, unremarkable in size and shape, sitting in no special place. Each enlargement of the universe had come with the same quiet demotion of our own position within it, and this was not the last such demotion the century would deliver. The modern figure places Andromeda at about 2.5 million light-years, which makes it the most distant thing the unaided human eye can see. A faint grey smudge in a dark sky, its light having set out when the first members of our own genus were shaping stone tools in East Africa. Andromeda is the nearest large galaxy to our own, and the two of them are the giants of a small collection called the Local Group. Some 80 galaxies bound loosely together across about 10 million light-years, most of them faint dwarfs orbiting the two heavyweights, and the Local Group is itself nothing special. Beyond it, the galaxies gather in their thousands. The Virgo cluster, about 54 million light-years away, holds well over 1,000 of them. The Coma cluster, more than 300 million light-years out, holds thousands more. The scale keeps unfolding, each level revealing that the one before it was merely a detail. The clusters themselves gather into superclusters, and in 2014, a team led by Brent Tully traced the flow of galaxies through our own region and found that the Local Group and the Virgo cluster and everything around us for hundreds of millions of light-years all drift together toward a common gravitational center, part of a single enormous structure they named Laniakea, a Hawaiian word meaning immeasurable heaven. Laniakea contains something like 100,000 galaxies, and our whole galaxy is a single unremarkable speck near its outer edge, sliding slowly inward. At the heart of that flow lies a concentration of mass so great and so obscured behind the crowded band of our own Milky Way that astronomers can measure its pull without being able to see it clearly, and they call it, plainly, the Great Attractor. Even here, at the scale of superclusters, the theme repeats. The thing shaping the motion of 100,000 galaxies is something we feel by its gravity and cannot properly look at. And in between the clusters, the universe is emptier than anything we have yet described. In 1981, astronomers surveying the sky in the direction of the constellation Bootes found a region that seemed almost entirely vacant. A roughly spherical volume of space, some 330 million light-years across, held only about 60 galaxies, where the ordinary density of the cosmos would have predicted around 2,000. It became known as the Boots Void, one of the largest empty regions ever mapped. Consider what that emptiness would mean for anyone living inside it. If the Milky Way sat at the center of the Boots Void, our astronomers, looking out in every direction, would have seen no other galaxy at all with the instruments of the early 20th century. The nearest neighbors would have been too far away and too faint to detect. We would have concluded, quite reasonably, that our galaxy was alone, a single island of light in an infinite and otherwise empty dark, and we would have had no way to know we were wrong until our telescopes grew powerful enough, deep in the 20th century, to catch the faint smudges at the void's distant walls. And the Boots Void is not a freak. Voids of this kind are the single most common feature of the universe by volume. If you were to choose a point at random anywhere in the cosmos, the overwhelming likelihood is that you would land not in a galaxy, not near a star, not even within a filament of the cosmic web, but somewhere in the enormous hollow interior of a void, in a place so empty that the nearest galaxy might be tens of millions of light-years away in every direction. The bright web of galaxies that fills our photographs, the part we photograph precisely because it shines, occupies only a small fraction of the whole. Most of the universe is the space inside the bubbles, and the space inside the bubbles is very close to nothing at all. When we picture the cosmos as a glittering field of galaxies, we are picturing the exception and quietly editing out the rule, which is emptiness on a scale the mind was never built to hold. This turns out to be the shape of the universe at the largest scales, and it took decades of patient surveying to reveal it. The galaxies are not scattered evenly. They are strung along threads and gathered into sheets, with immense empty voids between them, so that the whole arrangement resembles a foam or a network of soap bubbles pressed together, the galaxies clinging to the thin surfaces where the bubbles meet, and the vast interiors standing empty. Astronomers call it the cosmic web. The bright matter, everything that shines, is confined to the membranes of that foam. Most of the volume of the universe is void. The threads of that web are more than an image. They are real structures, immense filaments of gas and dark matter stretching for hundreds of millions of light-years, along which galaxies are strung like beads of water on a spider's line, and along which fresh gas flows down into the galaxies to feed the making of new stars. The largest of these structures rank among the biggest things in the universe. One sprawling wall of galaxies, mapped by a great survey of the sky, runs for well over 1 billion light-years, a single connected arrangement of matter so vast that light itself takes more than 1 billion years to cross it. For a long time, these filaments held a puzzle of their own. When astronomers added up all the ordinary matter they could actually see in stars and glowing gas, they came up short, finding only about half of the ordinary matter that the early universe was known to have produced. The rest, the so-called missing baryons, seemed to have vanished. It took delicate observations to track it down, and the answer was that it had been hiding all along in the filaments of the cosmic web, spread out as gas too thin and too faint to glow brightly, warm and diffuse, threaded between the galaxies. Even the ordinary matter, it turned out, is mostly not in the bright places. It is mostly in the dark connective tissue that binds the web together. And the void is not truly nothing, only very nearly nothing. In the deepest cosmic emptiness, the density of matter falls to something like a single hydrogen atom in every 10 cubic meters. Within our own local group, the gas is denser, perhaps 1 atom per cubic meter. Set that against the air you are breathing as you lie here, which holds a number of molecules in every cubic meter so large that writing it out would mean a 2 followed by 25 zeros. The gulf between the air in this room and the space between the galaxies is not a difference of amount. It is a difference of kind. The universe is, overwhelmingly, empty. What we call matter, the stars and the worlds and the bodies, is the rare exception, a faint contamination in an ocean of nothing. Henrietta Leavitt did not live to see what her yardstick built. She died in 1921 of cancer before Hubble ever turned it on Andromeda. Years later, a member of the Swedish Academy began the process of nominating her for a Nobel Prize, not knowing she was already dead, and the prize is never given after death. Her name survives on the relation she found, and the pulsing Cepheids remain a fundamental rung of the ladder by which we measure the cosmos. But her work did more than enlarge the universe. When Hubble measured the distances to his Cepheids, he had also, along the way, been measuring something else about the galaxies that held them. He had been measuring their light itself, and the light was carrying a message that no one had asked it to carry. The spectral lines, the sharp fingerprints of elements like hydrogen and calcium, were shifted from where they should have been, pushed toward the red end of the spectrum. The galaxies were moving away from us. Not one or two of them, nearly all of them, and the more distant a galaxy was, the faster it was fleeing. A whole universe of galaxies was in flight, and at first no one could say why. The light from those galaxies did not arrive intact. It arrived stretched, and the first person to notice the stretching, years before anyone understood it, was working alone at a small observatory in Flagstaff, Arizona. His name was Vesto Slipher. At the Lowell Observatory, he had been photographing the spectra of spiral nebulae since 1912, and the work was brutally slow. The nebulae were faint, and to spread their weak light into a spectrum and still capture it on a photographic plate required exposures that ran across several nights. Slipher would sit in the cold dome, guiding the telescope by hand to follow the turning sky, keeping the faint smudge pinned precisely on the narrow slit of his instrument night after night for a single measurement. What the plates showed, when they were developed, were thin dark lines, and in nearly every nebula, those lines were shifted toward the red. By 1917, he had measured the motions of 25 spiral nebulae, and 21 of them were racing away at hundreds of kilometers per second, far faster than any star. The fastest, a nebula in the constellation Virgo, was fleeing at more than 1,000 kilometers per second. Slipher did not claim to have discovered anything grand. He reported, plainly, what his plates showed. The spirals were running. The reason they were running would have to wait for someone else to place the fact beside a second fact, and see the pattern that emerged. That connection was made at Mount Wilson, by Edwin Hubble, and a man whose path to the Great Telescope was as improbable as the discovery itself. Milton Humason had grown up in the mountains, left school at 14, and taken work as a mule driver, hauling equipment and supplies up the narrow switchback trail to the observatory as it was being built. He married the daughter of the observatory's chief engineer and took a job as a janitor on the mountain. From janitor, he became a night assistant, helping the astronomers run the telescopes in the dark, and then, quietly and by his own effort, he taught himself the delicate craft of the spectrograph until he became one of the finest astronomical photographers of his generation. By the late 1920s, Humason was capturing the spectra of galaxies so faint and so distant that a single exposure might run for 40 hours, spread across many nights, with Humason at the eyepiece the entire time in the freezing dark, nudging the telescope by hand to hold the galaxy still. He drew spectra out of objects millions of light years away, and the redshifts he measured, together with Slipher's, became the raw material for one of the most important graphs ever drawn. In 1929, Hubble and Humason published it. On one axis, the distance to each galaxy, measured with Cepheids and other markers. On the other, the galaxy's speed away from us, read from the redshift of its light. The points did not scatter at random. They fell along a straight line. The farther a galaxy was, the faster it receded, and the relationship was proportional. Double the distance, double the speed. The number that described the slope of that line came to be called the Hubble constant, and it measured the rate at which the whole universe was expanding. Hubble's first value was far too high, because his distance measurements were still crude, but the relationship itself was unmistakable, and it did not go away. The universe was not a fixed and eternal stage. It was growing. It is hard, from where we stand now, to feel how strange this was. Before 1929, nearly every astronomer alive took for granted that the universe was static and eternal, the same on the largest scale forever. Einstein himself had run into the problem more than a decade earlier. When he completed his general theory of relativity in 1915, his own equations told him that the universe could not sit still, that it must be either expanding or contracting under its own gravity. This seemed so obviously wrong that Einstein added an extra term to his equations, a cosmological constant, tuned precisely to hold the universe motionless. He would later describe it as the greatest blunder of his life. The mathematics had been trying to tell him the truth, and he had reached in and silenced it. because a moving universe was more than anyone was prepared to believe. The person who was prepared to believe it was a Belgian priest and physicist named Georges Lemaitre. In 1927, 2 years before Hubble's paper, Lemaitre had independently derived the expansion from Einstein's own equations and had published it in a small French-language journal where almost no one read it. He went further than the equations. If the universe is expanding now, he reasoned, then it was smaller in the past, and if you run the film backward far enough, everything must once have been compressed into a single, dense, hot origin, which he called the primeval atom. When Lemaitre described his idea to Einstein in person, Einstein's reply was cutting. "Your calculations are correct," he told the young priest, "but your physics is abominable." It took Hubble's data, 2 years later, to prove that Lemaitre's abominable physics was simply the truth. Lemaitre lived long enough to be vindicated in full. Decades after his lonely paper, gravely ill and near the end of his life, he received word that the afterglow of his primeval atom, the faint radiation left over from the hot beginning he had proposed, had at last been found, direct evidence of the very thing he had reasoned his way to from Einstein's equations alone. He died only a few years later, a priest who had insisted, against the fashion of his age, that the universe began, and who had been told his physics was abominable by the greatest scientist of the century, and who turned out to be right. The universe had a beginning. Today, the evidence for that hot beginning, the event we call the Big Bang, is overwhelming and comes from many independent directions, and we can put an age to it. 13.8 billion years, the universe began in a state we still do not fully understand, and it has been expanding and cooling ever since. The idea did not win easily. For much of the 20th century, a serious rival held the field, the steady-state theory, which proposed that the universe had no beginning at all, that it expanded, but had always looked much the same, with new matter quietly created to fill the widening gaps. Its most brilliant champion was the British astronomer Fred Hoyle, a fierce and original thinker who never accepted the Big Bang, and in fact, gave it its name by accident. Speaking on the radio, Hoyle referred dismissively to the rival notion that everything had begun with one Big Bang, meaning the phrase as mockery. The name stuck, and the theory he was mocking is the one that won. What defeated the steady-state picture, in the end, was that oldest light. Back in the 1940s, the physicist George Gamow and his colleagues Ralph Alpher and Robert Herman had worked through the consequences of a hot beginning and predicted that it should have left behind a faint bath of radiation, filling all of space, cooled by now to just a few degrees above absolute zero. The prediction was made and then quietly forgotten for nearly 20 years. When that radiation was finally found, entirely by accident, the steady-state theory had no good answer for it, and the debate was effectively over. The universe had a beginning, and it had left us a receipt. It helps to be careful about what expansion actually means, because the obvious picture is wrong. It is tempting to imagine the galaxies as fragments hurled outward from an explosion, flying apart through a pre-existing empty space. That is not what is happening. The galaxies are, for the most part, not moving through space at all. Space itself, the fabric in which they sit, is stretching, and it carries them apart the way currents carry driftwood. The old and imperfect image is a balloon with coins glued to its surface. As you inflate the balloon, every coin moves away from every other coin, and the more distant two coins are, the faster the surface between them stretches them apart. Yet no coin is crawling across the rubber. The rubber itself is growing. In the same way, the red shift of a distant galaxy is not really the familiar shift of a passing siren. It is the light itself being stretched, its waves drawn out longer and longer as the space it is crossing expands beneath it during the millions or billions of years of its journey. The light does not arrive carrying the galaxy's speed. It arrives carrying the history of the space it crossed. This same picture has recently produced one of the sharpest puzzles in modern cosmology, and it turns on that single number, the rate of expansion. It should be possible to measure that rate two different ways and get the same answer. One way looks at the early universe, reading the expansion rate out of the fine pattern of the cosmic microwave background. That oldest light, as mapped by the Planck satellite, that method gives a value of about 67 kilometers per second for every megaparsec of distance. The other way works in the nearby universe, climbing the distance ladder from Cepheids to supernovae, refined in recent years by Adam Riess and his team using both the Hubble and the Webb telescopes. That method gives a value closer to 73. The two numbers should agree. They do not, and the gap between them is now far too large and too well measured to be waved away as error. When the Webb telescope came online, many astronomers expected it to close the gap, to expose some flaw in the Cepheid measurements that would pull the local number down into agreement. It did not. The Webb data sharpened the local measurement and left the disagreement standing. The picture on the local side is not perfectly unanimous. One group led by Wendy Friedman, using a different kind of stellar yardstick, finds a value nearer the middle, more consistent with the early universe number, but the central tension has now survived every serious attempt to make it vanish. Either one of our two best methods hides a mistake no one has found, or the standard model of the universe is missing something, some new ingredient in the early cosmos, some new physics we have not yet named. We do not know which. It is one of the most active frontiers in the field. The proposed solutions are many, and none has yet won. Some physicists suspect a brief burst of a new kind of dark energy in the first moments after the Big Bang, active only for a short window, and then gone, which would have subtly changed the early universe in a way that shifts the number derived from the oldest light. Others look for new properties of the ghostly neutrinos, or for some slow change in the strength of gravity itself over cosmic time. Each proposed fix solves the Hubble tension, but tends to spoil the fit to some other exquisitely measured quantity, so that pushing the problem down in one place makes it bulge up in another. What makes this more than an accounting dispute is what hangs on it. The expansion rate sets the size, the age, and ultimately the fate of the universe. If the two numbers cannot be reconciled without new physics, then the standard model that has served cosmology so well, the model that so beautifully explains the oldest light and the growth of structure, is incomplete in some fundamental way we have not yet grasped. A discrepancy of a few kilometers per second in a universe billions of light years across may be the loose thread that unravels part of the whole picture. We are, at the moment, still pulling on it. The other great pillar of the Big Bang, the cosmic microwave background itself, was found entirely by accident, and the accident began with an unshakable hiss. In 1964, two radio astronomers at Bell Labs in New Jersey, Arno Penzias and Robert Wilson, were preparing a large horn-shaped antenna for experiments in satellite communication. Wherever they pointed it, at whatever blank patch of empty sky, they picked up a faint background noise they could not get rid of. They checked the electronics. They looked for interference from nearby New York City. They found a pair of pigeons nesting inside the horn and evicted them, and scrubbed out the residue the birds had left behind. Still the noise remained, coming from every direction of the sky, day and night, at all seasons, equivalent to a temperature just a few degrees above absolute zero. What they were hearing, though they did not yet know it, was the afterglow of the Big Bang, the cosmic microwave background, stretched now into faint microwaves. Not far away, at Princeton, a group of physicists led by Robert Dicke had calculated that a hot early universe should have left exactly such a glow, and had begun building an instrument to look for it. When Dicke heard about the noise at Bell Labs, he put down the phone and told his colleagues, simply, that they had been scooped. Penzias and Wilson, who had been trying to eliminate the very thing others were racing to find, received the Nobel Prize for it in 1978. Finding the glow was only the beginning. Reading it took 3 more generations of instruments, each one a landmark. In 1992, a satellite called COBE measured the spectrum of that ancient light and found it to be the most perfect example of pure heat radiation ever observed anywhere in nature, exactly as the Big Bang predicted, and it detected, for the first time, faint ripples in the glow, tiny variations of a few parts in 100,000 from one patch of sky to another. The two scientists who led that first satellite, John Mather and George Smoot, received the Nobel Prize for it, and Smoot described the faint ripples they had found, with only slight exaggeration, as like seeing the face of God, meaning that they were looking at the very seeds of all later structure printed into the universe when it was less than 1 million years old. Those ripples were the seeds of everything. The slightly denser regions would go on, over billions of years, to collapse under gravity into galaxies and clusters, while the slightly emptier regions would thin out into the great voids. A later satellite, called WMAP, mapped those ripples in far finer detail, and the Planck satellite finer still, until the baby picture of the universe became sharp enough to read the exact recipe of the cosmos from it. And that recipe held a demand that could not be met by ordinary matter alone. The pattern of the ripples, the way the hot and cold patches were sized and spaced, could not have grown out of the primordial plasma in the time available unless something else had been there from the start, something that felt gravity but ignored light, something that had already begun gathering into clumps while the ordinary matter was still trapped and glowing in the fog. The oldest light we possess carried, written into its faint unevenness, the fingerprints of the invisible. And to find out what left those fingerprints, we have to follow a different thread, one that begins not in the early universe but in the turning of galaxies close to home, in the work of a handful of astronomers who noticed that the visible cosmos does not weigh nearly enough. The missing mass did not first reveal itself in the graceful spin of a single galaxy. It showed up in a swarm, a great cluster of galaxies bound together by gravity, where the speeds of the individual members told a story that their light flatly refused to support. The man who read that story was a Swiss astronomer at the California Institute of Technology named Fritz Zwicky, and almost no one at the time was willing to listen to him. Zwicky was brilliant, abrasive, and widely disliked. He was fond of calling colleagues who annoyed him spherical bastards, on the grounds that they looked like bastards from every possible angle. He also had a maddening habit of being right about things that no one would accept for decades. He and a collaborator coined the very word supernova to describe the most violent stellar explosions. In 1934, he proposed that such an explosion would leave behind an incredibly dense remnant made of neutrons, an idea confirmed only decades later when the first neutron stars were found. He predicted that massive galaxies could bend light and act as lenses, which no one confirmed until long after his death. Dark matter was simply one more thing he saw before the rest of the field was ready. In 1933, Zwicky turned his attention to the Coma Cluster, that same rich gathering of galaxies more than 300 million light-years away. He used a piece of classical physics called the virial theorem, which relates how fast the members of a bound system are moving to the total mass required to hold them together against their own motion. He measured the speeds of the galaxies in the cluster from their redshifts, and the speeds were enormous, hundreds of kilometers per second. Then he calculated how much mass the cluster would need to keep those fast-moving galaxies gravitationally bound rather than flying apart, and he compared it to the mass he could account for from the light of all the visible galaxies put together. The two numbers were not close. The cluster needed vastly more mass than its light could explain. Zwicky's first estimate put the missing factor at several hundred, later revised downward as the distance scale of the universe was corrected, but the qualitative result was solid and it never went away. There was mass in that cluster that gave off no light whatsoever, and there was far more of it than anything that shone. He called the unseen substance, in his native German, dark matter. Almost no one paid attention. Zwicky published in a Swiss journal, in German, and the astronomical world had other things on its mind. A year earlier, the Dutch astronomer Jan Oort, the same Oort whose name is now attached to that distant shell of comets at the solar system's edge, had noticed a smaller version of the same problem closer to home. Studying the way stars bob up and down through the plane of the Milky Way, he found that the visible stars and gas did not seem to provide enough gravity to explain their motion, hinting at some additional unseen mass in the disk of our own galaxy. Neither Oort's hint nor Zwicky's cluster could have prepared anyone for the truth. What they had each caught a corner of was not a small correction to the mass of the universe. It was the dominant form of matter in it, and the visible cosmos was the afterthought. It is worth sitting with how long this took to be believed, because it says something about how science actually moves. Zwicky published his cluster result in 1933. The problem he identified, which came to be called the missing mass, did not vanish, and other astronomers occasionally bumped into it over the following decades and noted it and moved on. But for nearly 40 years, almost no one treated it as urgent. It was easier to assume that the missing mass was ordinary matter that simply had not been counted yet, some faint gas or dim stars that better instruments would eventually reveal. A difficult, abrasive man had found an inconvenient result in an obscure journal, and the field, not unreasonably, waited for a simpler explanation to turn up. The simpler explanation never came. What finally forced the issue was not a single dramatic discovery, but the sheer accumulation of evidence. Rubin's rotation curves piling up galaxy after galaxy, the microwave background, the lensing, the colliding clusters, until the weight of it all became impossible to set aside. The dark matter was not accepted because one measurement was decisive. It was accepted because every new way of looking kept finding the same thing. The evidence that finally forced the issue arrived 4 decades later, and it came from the insides of ordinary spiral galaxies in the work of an astronomer named Vera Rubin. She had wanted the stars since childhood, watching them wheel past her bedroom window in Washington and, by her own account, unable to look away. She studied under Maria Mitchell's legacy at Vassar, and when she applied to do graduate work in astronomy at Princeton, the university simply refused to send her the application materials because its astronomy program did not admit women. She went to Georgetown instead, earned her doctorate, raised a family, and built, patiently, a career that would redraw the map of the universe. She was not a self-promoter. She chose, for much of her life, problems that other astronomers considered quiet and unglamorous, in part because the quiet corners were where a woman could work without being crowded out. Galaxy rotation was one of those quiet corners, until it was not. In the 1970s, Rubin worked with an instrument builder named Kent Ford, who had developed a spectrograph of exceptional sensitivity, sensitive enough to measure the motion of gas and stars at many separate points across the face of a spiral galaxy. Their method was direct. They would place the slit of the spectrograph along the visible disk of a galaxy and measure, point by point, how fast the material at each radius was orbiting the center, using the same redshift and blue shift that had revealed the flight of the galaxies. One side of the disk turns toward us, and its light shifts blue. The other turns away and shifts red. From the pattern, they could build a rotation curve, a simple graph of orbital speed against distance from the center. The observing itself was often done in difficult conditions. At one major observatory there was, at first, no women's restroom at all, the facilities having been built on the assumption that no woman would ever use the telescope. Rubin is said to have cut a paper skirt from a notebook and taped it to the little figure on a men's room door and gone on observing. The universe was waiting to be measured, and she was not going to be stopped by a sign. What the rotation curve should look like was, everyone agreed, entirely predictable. Most of a spiral galaxy's light comes from its bright central bulge and the crowded inner disk, so most of its mass, if mass follows light, should be concentrated near the center. In that case, stars far out at the edge, orbiting mostly empty space with the galaxy's bulk behind them, should move slowly, exactly as the outer planets of our solar system orbit the Sun more slowly than the inner ones. Neptune crawls, the Earth races. The orbital speeds in a galaxy should rise near the center and then fall away toward the rim. That was the prediction, clean and firmly grounded in the physics of gravity. Rubin and Ford aimed their spectrograph at the nearest great spiral, Andromeda, and began to measure. The inner points behaved. Then, as they worked their way outward, the numbers did something that made no sense. The orbital speeds did not fall. They flattened out and stayed flat, so that stars far out at the dim edge of the disk, where the visible light had thinned almost to nothing, were sweeping around the galaxy just as fast as stars near the brilliant core. In some galaxies, the curve even rose slightly toward the edge. Rubin's first instinct was distrust of her own data. She checked the instrument. She reanalyzed the measurements. She looked for any systematic effect that might be lifting the outer speeds artificially. She found nothing. The data were clean, and the curves were real. She published the flat rotation curve of Andromeda in 1970, and over the following years she and Ford measured dozens more spirals, and everyone told the same story. The curves refused to fall. There was only one way to make sense of it. There had to be far more mass in these galaxies than the stars and gas could account for, and that extra mass had to reach out well beyond the visible disk, out into the darkness where almost nothing shone, holding the fast outer stars in their orbits. If a galaxy contained only the matter we can see, its outer stars would long ago have flung themselves off into intergalactic space. They stay because something invisible is holding them, a vast spherical halo of unseen mass surrounding the bright disk, and extending, in many cases, 10 times farther than the stars themselves. The luminous galaxy, the beautiful pinwheel we photograph and admire, turns out to be a small bright ornament suspended at the center of an enormous dark sphere. For the Milky Way, the mass of that dark halo is roughly 10 times the combined mass of every star, every cloud of gas, every grain of dust in the galaxy. Everything that gives off light is a tenth, or less, of what is actually there. The rest emits nothing, absorbs nothing, reflects nothing. It gravitates, and otherwise it stays hidden. And it is not only far out at the galaxy's edge. The dark halo passes right through where we live. From the way the Sun and its neighbours move through the galaxy, astronomers can estimate how much dark matter must be flowing through our own corner of space. And the answer is that a small but steady density of it fills the room around you at this moment. In every volume of space the size of your own body, there is, on average, a tiny amount of dark matter. And because the whole solar system is sweeping through the galactic halo at hundreds of kilometers per second, that dark matter is streaming through you constantly, an unfelt wind of the invisible. Something like billions of dark matter particles may pass through your outstretched hand every second, depending on what the particle turns out to be, and not one of them, in your entire life, will leave a mark you could ever detect. This is what was meant, at the very beginning, by the thing passing through your body in the dark. It was never a metaphor, it was the literal wind of the halo, blowing through the walls and the floor and through you, on its way to nowhere. At first, many astronomers reached for an ordinary explanation. Perhaps the halo was made of perfectly normal matter that simply did not shine. Faint failed stars, cold gas, dead stellar remnants, drifting planets, small black holes. But when they went looking for these dark but ordinary objects, they found far too few to account for the mass. And a deeper constraint closed the door entirely. The amount of ordinary matter, the familiar stuff built from protons and neutrons, is fixed by the physics of the early universe and written into the cosmic microwave background, and that amount comes out at only about 5% of everything. The missing mass is roughly 5 times larger than all the ordinary matter combined. It cannot be made of protons and neutrons at all. Whatever it is something we have never held in a laboratory, never seen in a particle beam, never touched. And the same invisible substance that Rubin found threaded through the outskirts of Andromeda is the same substance Zwicky found holding the coma cluster together. The same substance the cosmic microwave background demands. The same substance that laid down the scaffolding on which every galaxy in the universe was built. It is not a local quirk. It is the main event, and the shining universe is the froth on top of it. Vera Rubin spent the rest of her life as one of the most respected astronomers alive, and she never received the Nobel Prize, though many in the field felt she plainly deserved one for confirming that most of the matter in the universe is invisible. She died in 2016. In her later years, she spoke often about the young women coming into astronomy behind her, and she cared, by all accounts, at least as much about opening the door for them as about the prize she was never given. There is a large new observatory built on a mountaintop in Chile to survey the entire southern sky again and again and map the dark matter across billions of galaxies, and it now carries her name. It is a fitting monument. She spent her life measuring the turning of galaxies and found, in that quiet, unglamorous work, that most of the universe is invisible, and the instrument that will chart that invisible universe more thoroughly than anything before it will do so under the name of the woman who first insisted the darkness was really there. By the time of her death, the question her work had forced open was no longer whether the dark matter existed. It was what, exactly, it was, and whether it was a new kind of substance at all, or whether the whole mystery might instead be a sign that our understanding of gravity breaks down in the faint outer reaches of galaxies. To decide between those two possibilities, astronomers needed a way to weigh the invisible directly, without leaning on the motion of stars, and the tool they would use had been predicted, decades earlier, by the same theory that gave us the expanding universe in the first place. Einstein's general theory of relativity, in its final form in 1915, made a prediction that even some of its admirers found close to mystical. Mass, Einstein said, bends the space around it, and light passing near a large mass will follow that curve, its path deflected as it skirts the gravitational well. Line up a distant source, a heavy foreground mass, and an observer just so, and the light of the distant source will be bent as it passes, smeared into arcs, or bent around both sides at once into multiple images of a single object. The foreground mass acts as a lens. The first confirmation came in 1919, when the British astronomer Arthur Eddington led an expedition to the island of Principe, off the west coast of Africa, to photograph the stars near the Sun during a total eclipse, when the Sun's glare was blotted out and the faint stars beside it became visible. He compared their positions to photographs of the same stars taken months earlier, when the Sun was elsewhere in the sky. Cleed, the stars near the Sun had shifted, by precisely the amount Einstein's theory predicted. Their light bent as it grazed the Sun's gravity. The announcement made Einstein famous around the world overnight. It came barely a year after the end of the First World War, and there was something quietly remarkable in the fact that a British expedition had crossed the world to confirm the theory of a German-born physicist, science reaching across the wreckage of a war between their nations to test an idea on its merits alone. The newspapers carried the result on their front pages. A private, unknown professor became, in a matter of days, the most famous scientist alive. And beneath the fame was the solid fact that mattered here: humanity's first direct proof that gravity can bend the path of a ray of light, the very effect that would later let us weigh the invisible. It was Fritz Zwicky, again, who saw where this could lead. In 1937, only a few years after his dark matter paper, he pointed out that whole galaxies, with their immense mass, should be able to lens the light of more distant objects behind them, and that measuring the bending could reveal the true mass of the lensing galaxy, including any part of it that was invisible. As with so much of what Zwicky proposed, the idea sat unused for a generation. The first real gravitational lens was not found until 1979, when astronomers observed what looked like two identical quasars, sitting suspiciously close together in the sky, with spectra so alike that they could not be a coincidence. They were not two quasars. They were a single distant quasar whose light had been split into two images by the gravity of a galaxy lying between it and us. The prediction had become an observation. In the years that followed, astronomers found the full range of the effect Einstein had described. Where the alignment between a distant source and a foreground mass is very nearly perfect, the source's light is bent evenly around all sides of the lens and smeared into a complete circle, a luminous ring of light surrounding the dark mass at its center. These are called Einstein rings, and each one is a distant galaxy whose image has been wrapped, by gravity, entirely around an object in front of it. The great space telescopes have now photographed many of them, glowing loops of ancient light bent around unseen mass, and each is a small proof, written across the sky, that Einstein was right about how gravity treats light. Since then, gravitational lensing has grown into one of the most powerful tools in astronomy, and it comes in two strengths. The dramatic version is strong lensing, when the foreground mass is very large and the alignment very good, as with a massive cluster of galaxies. The light of objects directly behind it is stretched into long luminous arcs, sometimes bent almost entirely around the cluster into a ring. By modelling the exact shapes and positions of these arcs, astronomers can weigh the cluster and map how its mass is distributed. And in cluster after cluster, the mass revealed by the lensing is far greater and spread far wider than the visible galaxies and the hot gas can explain. The lens is always heavier than the light. The subtler version is weak lensing, and it is subtle almost to the point of magic. Most distant galaxies, seen across large stretches of sky, are oriented at random, their apparent shapes pointing every which way. But when a great mass lies between those galaxies and us, its gravity bends their light just slightly as it passes, and stretches each background galaxy's image into a faint ellipse, tilted preferentially in one direction. No single galaxy shows the effect clearly, but by measuring the shapes of many thousands of background galaxies and looking for a slight, shared, systematic distortion, astronomers can reconstruct the mass that must lie in front of them, even if that mass gives off no light at all. Weak lensing is a way of seeing the invisible purely by the way it warps the view of everything behind it. It maps the dark matter directly, by its gravity, with no need to assume anything about stars or orbits. There is a further gift in all this bending of light. A massive cluster does not only distort the galaxies behind it, it magnifies them, focusing their light the way a lens does, so that a great cluster of dark matter becomes an enormous natural telescope hanging in space. Astronomers have learned to point their instruments at exactly the right spot behind a massive cluster, and use the cluster's gravity to magnify galaxies far too distant and faint to see any other way. Some of the earliest galaxies ever observed, formed only a few 100 million years after the Big Bang, were caught this way, their light amplified many times over by the dark matter of a nearer cluster. The invisible substance, which gives off no light of its own, has become one of our best means of gathering the light of the very first galaxies. We use the dark matter to see what we otherwise could not, even as it refuses to show us what it is. The single most decisive image in this whole story came from a system that astronomers call, informally, the bullet cluster. It is not one cluster, but two, caught in the act of colliding. Nearly 4 billion light-years away, a smaller cluster of galaxies has plunged straight through a larger one at enormous speed. To understand what the collision reveals, you have to know that a cluster of galaxies is not mostly galaxies. Most of its ordinary matter is not locked up in the stars at all, but spread out between the galaxies as an immense cloud of hot gas, so hot that it glows in X-rays. When the two clusters crash together, their individual galaxies, being tiny and far apart, mostly sailed straight past one another untouched, like two swarms of gnats passing through each other. But the two great clouds of hot gas, filling the space between the galaxies, could not pass so cleanly. They collided and dragged and slowed and piled up in the middle, and the X-ray telescopes, chiefly the Chandra Observatory, caught them there, glowing between the two clusters, one of them shaped like a blunt bullet, which gave the system its name. Now the crucial test. If a cluster's mass is simply its ordinary matter, then most of the mass should sit where most of the ordinary matter sits, which is in that hot gas piled up in the center. So the gravity of the cluster, measured by weak lensing, should be centered on the gas. In 2006, a team led by Douglas Clow mapped the mass of the bullet cluster by weak lensing and set it against the X-ray map of the gas. The two did not match. The mass was not where the gas was. The mass had split into two clumps, one moving with each cluster of galaxies, sailing on ahead of the slowed and stranded gas exactly as the galaxies had. In other words, most of the mass of the cluster had passed straight through the collision without slowing down, ignoring the pile-up entirely, the way the galaxies did and the gas did not. That is precisely the behavior expected of dark matter, a substance that feels gravity but barely interacts with anything, not even with itself, so that it flies through a collision unimpeded while ordinary gas grinds to a halt. The bullet cluster shows gravity concentrated where almost nothing shines, torn away from the ordinary matter that ought to carry it. It is the closest thing we have to seeing dark matter with our own eyes, and it is very hard to explain any other way. And it is not the only one. Since the bullet cluster was measured, astronomers have found other colliding clusters that tell the same story, each a separate cosmic accident caught at a different angle, each showing the same clean separation of the gravity from the glowing gas. In one system, the collision seems to have happened almost along our line of sight. In another, two clusters have passed through each other and are now falling back together. In a strange case nicknamed the cosmic train wreck, the picture is messier and has invited real debate. But the overall pattern, across many such wrecks, holds. When clusters collide, the ordinary matter piles up and glows, and the bulk of the mass sails on ahead, indifferent, exactly as a cloud of barely interacting dark matter should. No single collision is proof. Together, they are as close to a direct sighting of dark matter's behavior as anything we possess, a repeated natural experiment that a mere change in the law of gravity struggles to reproduce. Because there is another way to read all of this, and it deserves an honest hearing. Perhaps there is no missing substance at all. Perhaps instead our law of gravity is simply wrong out at the very low accelerations found in the outskirts of galaxies. In 1983, an Israeli physicist named Mordechai Milgrom proposed exactly that. His idea, called modified Newtonian dynamics, keeps gravity exactly as Newton and Einstein described it for the strong pulls we know well, but adjusts it very slightly in the regime of extremely weak acceleration, so that stars at the edges of galaxies feel a stronger tug than standard gravity would give them, and therefore orbit faster, with no need for any invisible halo, On the scale of individual galaxies, the idea works remarkably well. With a single adjustment, it reproduces the flat rotation curves that Rubin measured, often more neatly than dark matter models do, and it correctly predicted certain regularities in galaxies that were only confirmed later. For spiral galaxies taken one at a time, it is a genuinely strong competitor. But the universe is not only galaxies, and this is where the modified gravity idea runs into trouble. The bullet cluster is a hard problem for it, because a simple change to the law of gravity should keep the extra pull centered on the ordinary matter, on the gas, and yet the gravity there is plainly offset from the gas, sitting instead with the collisionless clumps, exactly as a substance of dark matter would be. Harder still is the cosmic microwave background. The precise pattern of its ripples, the relative heights of its peaks, encodes how much ordinary matter and how much non-ordinary matter the early universe held. And that pattern simply cannot be reproduced without a large amount of matter that gravitates but does not interact with light. A change to gravity does not naturally supply that. The most honest summary is this: modified gravity is a minority position, held by a small and serious community of researchers whose work has sharpened everyone's thinking and forced the dark matter models to prove themselves. It succeeds beautifully on the scale it was built for, and it struggles on every larger scale. Dark matter, as a real, cold, barely interacting substance, explains the galaxies, the cluster or bullet cluster, the microwave background, and the whole architecture of the cosmic web, all at once with a single idea. It has exactly one great unsolved problem of its own. In more than 40 years of looking, no one has ever caught a single particle of it. Before we go underground to look for that particle, it is worth seeing just how thoroughly the invisible has already been weighed, because the case for it is built from more than the turning of galaxies. Return, one more time, to the oldest light. The cosmic microwave background is a snapshot of the universe as it was 380,000 years after the beginning, at the instant the fog cleared and light broke free. But in the moments before that, the universe was a plasma, and that plasma was ringing. Gravity was pulling the ordinary matter inward, trying to collapse it into the denser spots, while the pressure of the trapped light pushed back outward, and the tug of war set up sound waves, real acoustic waves, rolling through the primordial fire. When the light finally escaped, those waves were frozen in place, printed into the pattern of hot and cold patches across the sky. The characteristic sizes of the patches, the way they cluster at particular scales, are the frozen wavelengths of the sound that filled the newborn universe. The heights of the peaks in that pattern are a readout of what the universe is made of. In the year 2000, an experiment called Boomerang, an instrument flown on a balloon high over Antarctica, measured the first and largest of those peaks, precisely enough to answer a very old question. And the answer was that space, on the largest scale, is flat. Later, the finer maps from the WMAP and Planck satellites measured the smaller peaks, and it is one of those, the third peak, that speaks directly to the dark matter. Its height can only be as tall as it is if the early universe contained a large amount of matter that gravitated but did not feel the pressure of the light. Matter that could keep collapsing while the ordinary matter was still held up by radiation. That is the non-ordinary dark matter, and the microwave background pins its quantity at about 27% of everything, against just 5% for the ordinary matter we are made of. Two entirely separate lines of evidence, the turning of nearby galaxies and the ringing of the infant universe, arrive at the same invisible substance, and very nearly the same amount of it. The same ancient sound left a second fingerprint, this one written across the sky in the arrangement of galaxies themselves. Because the sound waves in the early universe all travelled for the same length of time before the fog cleared, they all reached the same characteristic distance, and that distance became imprinted as a slight preferred spacing between galaxies, a faint tendency for pairs of galaxies to sit a particular length apart, about 150 megaparsecs. This preferred spacing acts as a ruler laid across the cosmos, a known length that astronomers can measure at different distances and therefore at different ages of the universe, tracking how the expansion has changed over time. It is called the Baryon acoustic oscillation, and it is the tool that our newest surveys use to weigh the expanding universe, a fossil of the primordial sound, still legible in the sky billions of years later. And when astronomers build the universe inside a computer, they find they cannot make it look right without the dark matter. Simulations of cosmic history start with a distribution of dark matter and let gravity work over billions of years, then let the ordinary gas fall into the wells the dark matter carves. What emerges is a cosmic web of filaments and clusters and voids that matches the real sky in detail. Leave the dark matter out, and the simulated universe comes out wrong, too smooth, too empty of structure, unable to build the great clusters and walls we actually see. The galaxies exist because the dark matter went first, gathering into halos, digging the gravitational wells into which the ordinary matter later fell to cool and condense and light up. We know where it is. We know how much of it there is. We know it is cold, meaning its particles move slowly, and that it barely interacts with anything, and that it is not made of the ordinary stuff of atoms. We know it was present from the very beginning and that it built the frame on which everything hangs. We know a great deal about the dark matter. We simply do not know what it is. And so, having weighed the invisible from every direction, we go looking for a single piece of it. To have any hope of catching one, you must go deep underground. Not into a cellar, and not even into an ordinary mine, but into a chamber carved beneath a full kilometre or more of solid rock, because the surface of the Earth is under a constant soft rain of particles from space, and that rain would drown any signal. Down where the rock has filtered the sky to near silence, you build a detector out of the quietest materials that exist. Xenon so pure it barely glows, or crystals of germanium grown to a purity that took years to achieve. And you cool the whole thing to within a hair of absolute zero. You wrap it in layers of shielding, lead, and plastic, and sometimes ancient lead salvaged from Roman shipwrecks that sank 2,000 years ago, prized because its own faint radioactivity has had all that time to fade away. And then you wait. You wait for one particle of dark matter, out of the countless numbers streaming through the Earth every second, to strike one atomic nucleus in your detector hard enough to make it recoil, producing a single tiny flash of light, a single faint pulse of charge, distinguishable from all the ordinary background only by its energy and by the fact that nothing else in the known universe should have caused it. This experiment, in various forms and in various deep laboratories around the world, has been running for more than 40 years. It has not yet seen the thing it was built to find. There is something almost devotional about these places. Whole teams of people descend each day in cage lifts, a kilometre down into the rock, to tend instruments cooled near the coldest temperature in the universe, shielded by ancient lead and by the mountain itself, all to sit in the deepest silence humanity can build and wait for a single touch from something that has never announced itself. Careers are spent this way. People give 30 years to the waiting, and the detectors grow larger and quieter with each generation, and the silence, so far, has only deepened. It is one of the strangest vigils in the history of science, an entire discipline holding perfectly still, underground, listening for a whisper that may or may not ever come. The particle these detectors were designed to catch has a name, the WIMP, standing for Weakly Interacting Massive Particle. Massive, meaning perhaps tens or hundreds of times the mass of a proton, and weakly interacting, meaning it responds to gravity and to the weak nuclear force, the same feeble force behind certain kinds of radioactive decay, but to nothing else. A particle like that could pass through a light year of solid lead with only a modest chance of ever touching anything. But very rarely, on the scale of a handful of events per year and a ton of detector, one might clip a nucleus and leave its faint mark. The reason this particular candidate was pursued so hard for so long is a coincidence that theorists found almost too pretty to be accidental, sometimes called the WIMP miracle. If a particle exists with roughly the mass and the interaction strength that the physics of the early universe would naturally produce, then, as the young universe expanded and cooled, such particles would have annihilated one another until just the right number were left over, and that leftover number comes out almost exactly at the amount of dark matter we actually measure, a particle at a scale that our physics already had reasons to expect would produce, all on its own, the right amount of dark matter. It seemed like the universe pointing at an answer. So the experiments were built, generation after generation, in the deep laboratories beneath the Gran Sasso mountain in Italy, in a former gold mine in South Dakota, inside a mountain in Japan. Each new detector held more of the target material and shut out more of the background than the one before it. a lineage of ever larger and ever quieter tanks of liquid xenon and crystal. Each one reached deeper into the range where the WIMP was supposed to be hiding, and each one found nothing. The silence has now grown so complete that the detectors have pushed past most of the parameter space the WIMP miracle pointed to, and they are approaching a strange final barrier, sometimes called the neutrino fog. The detectors have become so exquisitely sensitive that they are beginning to register the ghostly neutrinos streaming out of the sun, particles almost as reluctant to interact as the dark matter itself, and those solar neutrinos produce faint signals nearly indistinguishable from the dark matter signal being hunted. The searchers built instruments so quiet they can hear the sun's ghosts, and still no dark matter has spoken. Nor has it appeared where physicists hoped they might make it themselves. The Great Particle Collider at the European Laboratory near Geneva, the machine that found the Higgs particle, was expected by many to produce WIMPs directly in its collisions, smashing ordinary matter together, hard enough to conjure the dark particle into brief existence. It has run for well over a decade at the energies where the theory said the WIMP should live. It has found the Higgs and much else, and no sign whatsoever of dark matter. The convergence that once seemed almost promised, particle physics and cosmology meeting at a single answer, has not happened. From three directions at once, the deep detectors underground, the collider in Geneva, and the search for the glow of dark matter annihilating in the sky, the simplest and most beautiful version of the theory has been pushed into a smaller and smaller corner, and in that corner it has stayed stubbornly silent. Some physicists now suspect the dark matter is something quieter and stranger than the tidy WIMP, a particle that speaks only through gravity, or an entire hidden family of particles with forces of their own that never touch the ordinary world at all. Others hold out for one of the deep detectors, in its final and largest form, to catch the faint recoil at last before the neutrino fog closes over the search for good. There is one experiment that says it has heard something, and it has become the great unresolved argument of the field. Deep in the Gran Sasso laboratory, a detector run for decades by an Italian physicist named Rita Bernabei, and her team has reported a signal that no one else can either confirm or dismiss. Their detector does not simply wait for a single strike. It watches for a rhythm across the year, as the Earth orbits the Sun, and the whole solar system sails through the galaxy's halo of dark matter. The Earth should run a little faster into the dark matter wind in one part of its orbit, and a little slower in the opposite part, so the rate of dark matter strikes ought to rise gently in early summer and fall in winter, a small annual tide. Bernabei's experiment has seen exactly that annual tide, in the right phase, repeating year after year for more than 2 decades, with a strength that is very hard to blame on chance. And yet no other detector, using different materials, has ever seen the matching signal. Every attempt to reproduce it elsewhere has come up empty. Most physicists suspect that some overlooked seasonal effect, a slow drift of temperature or humidity, or trace radioactivity that also follows the calendar, is masquerading as a dark matter tide. But no one has proven it, and Bernabei's team stands by the result, and so the anomaly endures, neither confirmed nor killed, a single, stubborn signal in a field of silence. The only fair way to settle it is to build another detector out of the very same material, the same kind of crystal, and see whether it too shows the annual tide. 2 such experiments have been built for exactly this purpose, one in Spain and one deep beneath a mountain in South Korea, using crystals grown to match. They have been running for several years now, watching for the same rhythm across the calendar. The early results have not reproduced the tide that Bernabei reported, which points, gently, toward the signal being some artifact rather than dark matter. But the crystals are not yet perfectly identical, and the collaborations have been careful not to claim more than the data allow, and so the argument is not quite over even now. It is a small, sharp illustration of how this science actually works. Not a single triumphant discovery, but one lonely, persistent claim and a slow, patient, years-long effort by other people to find out whether it is real. Most of the search for dark matter looks like this. Careful instruments in deep, quiet places, waiting, and honest disagreement about what the waiting has shown. While the great xenon detectors kept pushing into the neutrino fog, attention has been turning toward a completely different candidate, one that was not invented to explain dark matter at all. It is called the axion, and it was proposed in the late 1970s to solve an unrelated puzzle in the theory of the strong nuclear force. A puzzle about why that force appears to be perfectly balanced in a way it had no obligation to be. The particle that would fix the balance would be extraordinarily light, perhaps a trillionth the mass of an electron, and it would behave nothing like a heavy wimp, drifting through the cosmos more like a faint, pervasive field than a hail of individual bullets. If enough of them were made in the early universe, they could be the dark matter. The particle got its name from one of its proposers, the physicist Frank Wilczek, who borrowed it from a brand of laundry detergent on the grounds that the new particle cleaned up a stubborn problem in the theory. It is a rare case of a piece of fundamental physics named after soap. The chief experiment hunting it, called ADMX at the University of Washington, tries to coax an axion drifting through a strong magnetic field to convert into a faint whisper of microwave light, tuning slowly across the possible range of masses like a radio dial, searching for a single distant station. It has not found the station yet. The range it must search is enormous, and the work could take many more years. It may find nothing, or it may, one quiet day, land on a faint clear tone at a single frequency, and that tone would be the voice of the dark matter, heard at last. Other candidates have been raised and mostly ruled out. Heavier, hidden cousins of the ordinary neutrino would betray themselves by a particular glow of X-rays, and searches have found no such glow across most of the range they could occupy. Small black holes formed in the first instance of the universe, rather than from dying stars, were a tempting idea, until surveys watching for the brief brightening of stars as such a black hole drifted in front of them ruled out most of the possible masses, leaving only a narrow and awkward window. Some physicists have begun to wonder whether the whole framing has been too narrow. We have quietly assumed that the dark matter is a single kind of particle, sitting off to the side of the ordinary world, touching it only through gravity. But the ordinary matter we know is not one particle. It is a rich family, electrons and quarks and neutrinos and photons, bound together by several forces into the elaborate structure that builds atoms and chemistry and life. Why should the dark matter be any simpler? Perhaps there is an entire hidden sector, a whole shadow family of dark particles with dark forces of their own, dark interactions we would never see, an unseen counterpart to the ordinary world running silently alongside it, and coupled to us only through the faint pull of gravity. If that is so, then the dark matter is not a missing piece to be slotted into our theory. It is a second world, as complex perhaps as our own, sharing the same space and the same gravity and nothing else, forever sealed away from being seen. We have no evidence for such a shadow world, but we have no evidence against it either, and that, in itself, is a measure of how little we truly know. The list of what the dark matter is not grows longer every year, and that lengthening list is not a failure. It is a form of knowledge. Each null result carves away another possibility and tells us that whatever the dark matter is, it is even more retiring, even more thoroughly sealed off from the ordinary world than the simplest guesses assumed. The invisible has hidden itself from our most sensitive instruments for 40 years with a thoroughness that is almost a message in itself. And now we must turn to something stranger still, a second invisible, larger than the first, that we understand even less. If the dark matter is a mystery, the dark energy is closer to a chasm. It makes up about 68% of the entire contents of the cosmos, more than 2/3 of everything, and it is nothing like matter. It is not made of particles. It does not gather into clumps or halos. Strangest of all, it does not thin out as the universe expands. Ordinary matter and dark matter both dilute as space grows, spread ever more thinly through an ever larger volume. The dark energy does not. Its density appears to stay constant no matter how much the space stretches, as though empty space itself carried a fixed amount of energy in every cubic meter, an energy that is simply there and stays there, and never runs down. And this energy does not pull, it pushes. It is driving the expansion of the universe to speed up. That discovery came in the late 1990s, and it came as a shock to the people who made it, because they had set out to measure the opposite. Two teams of astronomers had taken up the same question, one of the oldest in cosmology. The universe is full of matter, and matter pulls on matter, so the expansion that began with the Big Bang ought to be slowing down, braked by the collective gravity of everything in it. The teams wanted to measure how much it was slowing, and thereby learn the universe's fate, whether it would expand forever, or coast to a halt, or one day reverse and collapse. To measure the slowing, they needed to compare the expansion rate long ago with the rate today, and for that they needed a reliable way to gauge vast distances. They found it in a particular kind of exploding star. A Type 1a supernova happens when a white dwarf, the dense burnt-out core of a star like the Sun, pulls matter from a companion star until it crosses a critical threshold of mass about 1.5 times the mass of the Sun, at which point a runaway thermonuclear detonation tears the whole star apart in a flash that can briefly outshine an entire galaxy. Because these explosions all detonate at nearly the same mass, they all reach nearly the same true brightness, which makes them a kind of standard candle. If you know how bright a thing truly is, and you see how faint it looks, you know how far away it is. There is even a small correction that makes them more reliable still. A relationship, discovered by careful observation, between how bright one of these supernovae becomes and how quickly it fades afterward, so that the brighter ones can be told apart from the dimmer ones and calibrated against each other. And because they blaze so fiercely, these supernovae can be seen across billions of light years, deep enough into the past to read the expansion history of the universe. One team, the Supernova Cosmology Project, was led by Saul Perlmutter at the Lawrence Berkeley Laboratory in California. The other, the High Z Supernova Search Team, was led by Brian Schmidt, working from observatories in Australia, with a young astronomer named Adam Rees carrying much of the analysis. Both teams hunted the same quarry the same way, imaging a patch of sky, returning weeks later, and subtracting one image from the other to reveal any new point of light that had flared up in between, a supernova caught in a distant galaxy. Then they raced to measure its brightness and its fading, competing and occasionally leapfrogging one another for telescope time. Both teams fully expected to find a universe that was slowing down. Both teams found the opposite. The distant supernovae were too faint, not by a little, and not at random, but systematically, and the effect grew with distance. Fainter meant farther away than expected, which meant the universe had expanded more than expected in the time since the light left them, which could only be true if the expansion had been speeding up rather than slowing down. Each team distrusted the result and hunted for the mistake. They checked whether cosmic dust might be dimming the supernovae. They checked whether supernovae long ago might have been intrinsically different from those nearby. They checked their calibrations and their instruments. The result held. In 1998, the two competing teams announced the same impossible finding within weeks of each other. The expansion of the universe is not slowing, it is accelerating. Something is overwhelming the collective gravity of all the matter in the cosmos and pushing space apart faster and faster. The fact that two rival teams, working separately, with different telescopes and different methods and every professional reason to hope the other was wrong, arrived at the same startling answer at the same time, is a large part of why the result was believed so quickly. Each team had been braced to catch the other in an error, and instead each confirmed the other's impossible finding. In the years since, the acceleration has been checked against completely independent evidence, the pattern of the oldest light, the clustering of galaxies, the ages of the very oldest stars, and it has held up under all of them. The exploding stars were not lying. In 2011, Perlmutter, Schmidt, and Rees shared the Nobel Prize for it. The simplest name for the something is the cosmological constant, and here the story circles back on itself, because the cosmological constant is precisely the term Einstein added to his equations to hold the universe still, and later renounced as his greatest blunder. In its modern form, it stands for the energy of empty space itself. Quantum physics tells us that a vacuum is not truly empty but restless, seething with particles that flicker into and out of existence too quickly to catch, and that restless vacuum should carry energy, and that energy should push space apart exactly as the dark energy does. The idea is elegant until you try to calculate how much energy the vacuum should hold. When physicists work it out from the known laws, they get a number larger than the observed dark energy by a factor with more than 100 zeros after it, 10 to the power of about 120 times too large. It is the worst disagreement between theory and measurement in the history of physics. Something is cancelling almost all of that vacuum energy, cancelling it to fantastic precision but not quite perfectly, leaving the faint residue that is now driving the cosmos apart. What performs that cancellation and why it stops just short of total, no one knows. Whatever the dark energy is, its behavior can be captured in a single number, the ratio of its pressure to its density. For a true cosmological constant, an energy inherent to space that never changes, that number is exactly -1, and the density stays perfectly fixed forever. If the number is a little different from -1, then the dark energy is not constant after all. It might slowly weaken over time, or, in a more violent possibility, grow stronger, tearing the universe apart with ever-increasing force. For years, every measurement returned a value indistinguishable from -1, consistent with a plain, unchanging cosmological constant, and the question seemed settled by default. That is no longer quite the case. The newest and most ambitious effort to read the expansion history is an instrument at Kitt Peak in Arizona called DESI, which uses 5,000 tiny robotic fibers, each swinging to catch the light of a single galaxy, to map the three-dimensional positions of tens of millions of galaxies and measure that fossil sound wave ruler at many different distances and epochs. The scale of the survey is worth pausing on. DEC is building the largest three-dimensional map of the universe ever made, charting the positions of tens of millions of galaxies and quasars, some of them so distant that their light set out when the universe was a fraction of its present age. Every one of those tiny robotic fibers repositions itself in seconds, and the whole array can capture the spectra of thousands of galaxies at once, night after night, gathering more measured redshifts in a single year than all of astronomy had accumulated in the century before it. When DC released its first cosmological results in 2024, they held a surprise. Combined with other data, the measurements showed a faint preference for a dark energy that changes over time, rather than one that stays constant. The signal was mild, and the honest response was caution, because mild signals often melt away when more data arrives. But when DEC released a larger analysis the following year, drawing on 3 years of observations, the preference had not melted away. It had grown stronger, reaching, in some combinations of the data, a level of around 3 to 4 standard deviations away from a simple constant. That is genuinely interesting, and it is not yet a discovery. Physicists hold to a strict threshold, 5 standard deviations, before they will say they have found something new, and the dark energy result has not reached it. It also depends on which supernova measurements are folded in, and some careful analysts argue that part of the effect may be a quirk of those particular measurements rather than a real change in the dark energy. But the hint has been enough to send theorists back to their equations, reconsidering models in which the dark energy is a slowly shifting field rather than a fixed constant of nature. If the dark energy really does change over time, then it is probably not the plain energy of empty space at all, but something more like a field that fills the universe and slowly shifts, a possibility that theorists have named quintessence, after the ancient idea of a fifth element beyond earth, water, air, and fire. A quintessence field could have been stronger in the past and be weakening now, or the reverse, and pinning down, which would tell us something entirely new about the laws of physics. We have no confirmed example of such a field. It remains, for now, a name attached to a hope. There is one more puzzle tangled up in all of this, and it is a strange one, sometimes called the coincidence problem. Matter thins out as the universe expands, while the dark energy holds steady. So for most of cosmic history, matter dominated, its gravity slowing the expansion, and only relatively recently, in the last several billion years, did the ever-diluting matter fall below the constant dark energy and let the acceleration take over, which means we happen to live very near the crossover, the brief cosmic moment when the two are roughly comparable, when the handover from a decelerating universe to an accelerating one is fresh. A few billion years earlier, and there would have been no acceleration to detect. A great many billions of years later, and the matter would be so thinned out, the galaxies so scattered, that the history could no longer be read. It is not clear whether this is a genuine clue, pointing at some deeper connection between the matter and the dark energy, or simply the kind of coincidence that any observer is bound to notice, since observers can only arise in an era rich enough in matter to have built stars and worlds. We do not know. We may be watching the first faint sign that the largest component of the universe is not the simple thing we assumed, or we may be watching a statistical ghost that will fade. It is, right now, an open question at the very front of the science. And it is not an idle question, because the dark energy holds the fate of everything in its hands. If it is a true constant, unchanging, then the expansion will accelerate without end, and the future is one of deepening isolation. The galaxies beyond our own small local group will recede ever faster, their light stretched ever redder, until one by one they slip past the horizon of what we can see and wink out of reach forever. If the dark energy instead grows stronger with time, the ending is faster and more brutal, a runaway in which the expansion eventually overwhelms not just the space between galaxies, but the galaxies themselves, then the stars, then the planets, then at the very last, the atoms, torn apart as space itself is ripped open. This violent ending has a name, the Big Rip, and its logic is grimly simple. If the dark energy grows steadily stronger without limit, then the outward push it exerts grows too, and structures that gravity currently holds together will, one after another, be torn apart. In order from the largest and most loosely bound to the smallest and most tightly bound, first the clusters of galaxies would be pulled apart, then individual galaxies would be dispersed, their stars flung into the widening dark. Then, in the final frantic moments, the push would grow strong enough to overwhelm the gravity holding a solar system together, and planets would be stripped from their stars. Then stars themselves would be pulled apart, then planets, and at the very last instant even atoms would be torn open, and space itself would be shredded, as the expansion rate raced to infinity in a finite time. The current measurements do not favour that violent ending, but they do not entirely forbid it either. Whether the universe ends in a slow, cold, endless dispersal or a sudden universal tearing depends entirely on the precise behaviour of the one component we understand the least. What is certain is that the dark energy, the majority of the universe, the force now shaping its whole future, is a name we have written over a blank. We have measured its effect with real precision. We have not the faintest idea what it is, and it is winning. The timescale on which all of this plays out is not a human scale, and it is not even a stellar one. It runs so far past the present age of the universe that the entire 13.8 billion years since the Big Bang, all of cosmic history so far, amounts to less than the first breath of the story. To speak of the deep future is to use numbers that have no handhold in anything we can touch. And yet the physics that governs the ending is, in its broad shape, the same physics that governs tonight. We can trace the path forward because the rules that describe the cooling of a dead star and the slow evaporation of a black hole are rules we already know. The details are uncertain, and some of the final steps hang on physics we have not yet confirmed. But the overall arc, the long fading of light and structure toward a final, featureless dark, is difficult to escape. The universe had a beginning. It will have an end, and that end, when it comes, will leave nothing behind. The first of the great endings, for anything living on the Earth, will be the death of the Sun, and it does not wait for the Sun to run out of fuel. The Sun is a middle-aged star, about 4.5 billion years old, and it has been slowly brightening its whole life. As the helium ash builds in its core, and the core contracts and heats, in roughly 1 billion years, the Sun will be about 10% brighter than it is today, and that is enough. The extra heat will push the Earth past a threshold from which there is no return, boiling the oceans into the air, and water vapour, itself, a powerful trap for heat, will drive the warming further until the Earth becomes a scorched world, its seas gone, its surface sterilised, whatever record of life once existed, reduced to chemical traces in ancient rock. This is not the distant red giant death. This is the near one, and it arrives while the Sun still looks, to any eye, entirely ordinary. Then, in about 5 billion years, the Sun will exhaust the hydrogen at its core and begin to swell. It will become a red giant, its bloated outer layers reaching out past the orbit of Mercury, past Venus, and possibly, depending on details the models still argue over, out to the orbit of the Earth itself. Whether or not the Earth is swallowed, it will be charred to bare rock, and then the Sun will shrug off its outer layers into space in slow glowing shells. and what remains at the center will be a white dwarf, a sphere of carbon and oxygen about the size of the Earth, but holding roughly half the mass of the Sun, so dense that a spoonful would weigh tons. It will shine at first from sheer leftover heat, blue-white and fierce, but it will have no fire of its own left to burn, and so it will cool over billions and then trillions of years, sliding down through white and yellow and orange and red until it becomes a cold, dark cinder, barely warmer than the space around it. The star that gave the Earth 4 billion years of light will end as a dead ember drifting in the dark. Around that same time, the sky itself will change beyond recognition, because the Milky Way is going to collide with the Andromeda Galaxy. This is not a guess. Measurements of Andromeda's motion, made with the Hubble and Gaia observatories, show the two galaxies falling toward each other, due to meet in something like 4 to 5 billion years. When they do, neither will survive as it is. The two spirals will tear through each other, their graceful disks pulled into long streaming tails of stars, and after a chaotic dance lasting hundreds of millions of years, they will settle into a single shapeless elliptical galaxy, a great featureless swarm of stars that some astronomers have already nicknamed Milkomeda. The two central black holes, our own Sagittarius A star and the far larger one at Andromeda's heart, will spiral together and merge in a burst of gravitational waves. Individual stars will almost never actually strike one another, because even in a galactic collision the stars are so absurdly far apart that they simply pass by the same emptiness we measured at the very start, now keeping the crash strangely gentle at the scale of any single sun. The Earth's dead cinder of a sun, if it endures, will likely be flung out into the outskirts of the new galaxy, orbiting under a sky where the familiar band of the Milky Way has been replaced by a dim, formless glow. The merger will flare with new stars for a while, as colliding gas clouds collapse and ignite. But the gas supply of any galaxy is finite. Each generation of stars locks more of it away in dead remnants and scatters the rest, and eventually there is not enough left to make new stars at all. The last stars to form will be the smallest and stingiest, the red dwarfs, which burn their fuel so slowly that a single one can shine for 10 trillion years. But even they must end. And so, in roughly 100 trillion years, the age of shining stars, the era we happen to live in, will come to a close. The final red dwarfs will gutter out, and the universe will be left with only the burnt remnants, the white dwarfs cooling toward black, the neutron stars, the black holes. The only light will be the rare, brief flash of two remnants colliding, and those flashes will grow rarer as everything drifts apart. The long twilight will have begun. Astronomers who study the far future divide it into eras, and the names are worth hearing, because they mark out just how brief our own moment is. We live in what they call the stelliferous era, the age of stars, the age of shining. It began a few 100 million years after the Big Bang, when the first stars caught fire, and it will last until roughly 100 trillion years from now, when the last red dwarf dies. That sounds enormous, and it is, but it is only the opening scene. After it comes the degenerate era, the long age of the dead remnants, the cooling white dwarfs and neutron stars and drifting black holes, an age that stretches on for a length of time that dwarfs the age of stars as thoroughly as the age of stars dwarfs a human life. After that, if protons decay, comes the black hole era, when even the dead stars have evaporated and only the black holes remain, slowly leaking themselves away. And after the last black hole is gone comes the final and by far the longest era of all, the dark era, which has no end, a cold thinning haze spreading forever through an ever emptier space. Set against that map, the entire age of stars, every sunrise that has ever happened, or ever will, is a single bright flicker near the very beginning of a night that goes on without limit. We are living in the flicker. It is the only part of the whole story in which anything is warm, or lit, or alive, and it is almost over before it has properly begun. If the proton is truly stable forever, then those dead stars will simply persist, cooling toward the temperature of empty space, becoming black dwarfs, spheres of cold, degenerate matter, emitting nothing at all. But some theories predict that even the proton is not eternal, that given enough time, an unimaginable span longer than 10,000 trillion years, Protons themselves will decay, dissolving into lighter particles. And if that is so, then all ordinary matter, every dead star and frozen world and drifting speck of dust, will slowly evaporate into faint radiation. Either way, the matter fades, and in the end, the only structures left standing will be the black holes, the most patient objects in the universe. Even they do not last. In 1974, Stephen Hawking showed that black holes are not perfectly black after all. Through a subtle quantum process at the very edge of the event horizon, a black hole slowly leaks radiation and slowly loses mass, and over almost inconceivable spans of time, it evaporates. For a black hole with the mass of a star, the process is fantastically slow, a lifetime longer than 10 to the power of 60 years, and for the giant black holes at the centers of galaxies, longer still, up to 10 to the power of 100 years. But the universe, by then, has nothing but time, one by one, across spans that make the entire history of stars look like a single spark. The black holes will shrink and grow hotter as they shrink, until in their final instant, each one flares with a brief, brilliant burst of radiation and is gone. And after the last black hole has evaporated, the universe will hold only a thin, cold, ever-thinning haze of particles and light, spreading into a space that keeps on stretching, cooling toward a temperature that approaches absolute zero but never quite arrives. No stars, no structure, no gradient of hot and cold that could drive any change or any life. This is the state physicists call the heat death, and it is not a bang or a collapse. It is an endless, silent, uniform fading, a universe grown perfectly quiet and perfectly dark, with nothing left happening anywhere, forever. Some have asked whether anything, any mind, any form of life or thought could survive into that long cold, and the honest answer bends toward no. Life, as far as we understand it, runs on differences, on a flow of energy from something hot to something cold, and it is exactly those differences that the heat death erases. A universe at perfect uniform temperature has no gradients left to drive anything, no way to do work, no way to store or process a single thought. The physicist Freeman Dyson once speculated hopefully that a sufficiently clever intelligence might stretch its experience across the growing cold by slowing itself down without limit, thinking ever more slowly to match the cooling universe, and so subjectively living forever on an ever thinner trickle of energy. It was a beautiful idea, but the discovery that the expansion is accelerating dealt it a heavy blow, because in an accelerating universe the usable energy does not merely thin out slowly, it drains away past the horizon and is lost for good, leaving even the most patient mind with a finite budget after all. It seems that the darkness is not only final but complete. Whatever wishes to think, or feel, or notice the universe at all, must do so now, in the brief lit window, or not at all. There is one last turn to this, and it may be the strangest thing in the whole account, because it concerns not the far future but the truth itself. Long before the heat death, in perhaps 1 trillion years, the accelerating expansion will have carried every galaxy beyond our own local group, past the horizon of what can be seen, their light stretched away into nothing. The cosmic microwave background, the afterglow of creation, will have been stretched so far that no instrument could ever detect it. And so a civilization arising in that far era, on some world in the merged remains of our galaxy, would look out at the sky and see only their own single galaxy, alone in an infinite and empty dark. They would find no other galaxies. They would find no afterglow, no redshift, no evidence of expansion, no trace of a beginning. Working with the finest instruments and the sharpest minds, they would conclude, correctly by all the evidence available to them, that the universe was static and eternal and consisted of their one island of stars and nothing more. Everything we have worked out, the flight of the galaxies, the Big Bang, the billions of other islands, the whole grand history, would be gone from the record, unrecoverable, erased by the same expansion that we can still, for now, measure. We happen to live in the brief window in which the evidence still exists. A civilization in our exact position, far enough into the future, would be profoundly and permanently wrong about the nature of reality, and it would have no way of ever knowing it. The universe is not only mostly hidden in space, it is mostly hidden in time and the era we occupy, the era in which the story is still legible, is not typical. It is a passing chapter, and the book is slowly closing itself. Remember the particles that were passing through your body when this began. They are still passing through you now. They passed through the walls of whatever room you are in, and through the whole thickness of the earth, and they never touched a single atom of you on the way. They were here before the video started, and they will be here long after it ends, and long after you do. They have been falling through this place since before the earth existed, since before the cloud of gas that became the earth existed, since the first galaxies gathered out of the primordial dark. They are the dark matter, the invisible frame on which everything visible is hung. You have never felt them. You never will. And yet you owe them your existence in a way that can be traced step by step, not as a figure of speech, but as a chain of physical cause. In the early universe, while ordinary matter was still a hot glowing plasma, trapped and unable to gather, the dark matter, which ignored the light, was already clumping under its own gravity, digging out the wells that would become the cradles of galaxies. When the fog finally cleared and the ordinary matter came free, it fell into those wells the dark matter had already prepared. The gas pooled and cooled and condensed, and the first stars caught fire inside dark matter halos billions of years before there was an Earth. And in the cores of those stars, and in their deaths, the heavier elements were forged, the carbon and oxygen and nitrogen and iron that no early universe contained, and that make up almost every atom of your body, more complicated than hydrogen. Every one of those atoms was cooked inside a star, and that star existed because the dark matter went first and made the place for it. You are, in the most literal and traceable sense, the downstream product of an invisible substance that will never once, in the whole history of the universe, be aware that you were here. That is the asymmetry that closes the story. The dark matter does not know you exist. It passes through you as though you were nothing, as though the entire lit-up world were a ghost, but you know it exists. You have weighed it, and mapped it, and buried detectors beneath mountains to wait for it, and worked out that it outnumbers everything you can see by 5 to 1. The vast majority of the universe cannot notice anything at all. The dark matter cannot. The dark energy cannot. The cold, dead stars and the empty voids and the evaporating black holes cannot. Only the thin, ordinary 5%, arranged in the fragile and temporary way that you are arranged, can look out at the enormous dark and understand even a little of what it is made of. The universe spent 13 billion years building, out of its rarest ingredient, something that could turn around and measure the rest. And here, tonight, in this room, in the dark, that is what is happening. The particles are still passing through you. They do not know, but you do. Good night.